Hello, Matt G for IYT here. Today we're looking at the full license mock examination number 1, version 1.6, and we've reached question 35, which reads, when travelling away from a transmitter on clear ground, it is noted that the field strength has halved. The power flux density can be expected to A. remain more or less constant, B. have reduced by a factor of about square root 2, C. have halved, or D, have reduced to a quarter of its initial value. So there's a couple of terms you've got to think about here. There is the field strength and then how that relates to the power flux density. And well, let's start by looking at field strength. And the field strength is a way of describing the intensity of an electric field at a particular point. So to sort of put that into practical terms, imagine if we have a capacitor with two plates, and those plates are, let's say, 1 centimeter apart, or 1/100th of a meter, and we apply to that capacitor 100 volts. So how would we calculate the strength of the field that exists between these two plates? And we'd use an equation E, which represents the electric field, equals V over D, or V, we always use V for voltage, and D represents the distance we're talking about. So let's take our calculator, and we said it was 100 volts divided by, and it was 1 centimeter, so let's do 1 divided by 100 to represent our 1 centimeter, and that gives us a field strength of 10,000, or 10,000 watts. Well, it's 10,000 volts per meter. We have 100 volts distributed over a distance of 1 centimeter. If we scaled that distance up to 1 meter, and we wanted to maintain the same electric field strength, then we would need to apply 10,000 volts, because this is 10,000 volts per meter. So our field strength describes the intensity of an electric field at a particular point. We can think of it as a scalar value because it is a single number. It is volts, remember, it's volts per meter. So what does the power flux density describe? Well, the power flux density describes the amount of power that is projected onto a square surface, a 1 meter square surface at a remote distance from the transmitter. There is a great diagram of this in the full license manual. We can see we've got a sphere which contains in the center of it an isotropic antenna, not a dipole, but it's the ideal isotropic antenna, the perfect antenna, and it is emitting a signal which is illuminating the inside of that sphere. And if we were to draw out a 1 meter square section anywhere on the inside of that sphere and measure the total amount of power that would be collected in that square, we would end up with a figure in watts per meter squared, and that is our power flux density. So our field strength is looking at the, you could think of it as looking at the potential difference over a distance, whereas the power flux density is looking at the amount of power projected onto a remote area, that remote 1 meter squared area. Now the relationship between these two numbers can be rather complex, but we can simplify it a little bit, and if we can think of the field strength as being like the side of a square, so a side of our square, volts per meter, whereas with our power flux density it is in fact a square meter, and we've got watts per meter squared, and they have a similar relationship as the side of a square and the area of a square. And we can demonstrate this with, if we say set the side length of our square to 8, so our length of one side of our square is 8, so the area of our square is going to be 8 squared, which is equal to 64. If we then halve, just as we're doing with the field strength here, if we then halve the side of our square, we make it 4, then the area of our square is then going to be 16, and the the kind of the factor difference, the 64 divided by 16 is 4. 16 is 64 divided by 4. So if we halve the field, if we halve the length of the side of our square, then the area of the square will divide by 4. And in the same way, if we halve the field strength, because of the very similar relationship that they have, then the power flux density will be divided by not 2, it will be divided by 4. So we can then compare that to our answers. When the field strength has halved, the power flux density it won't remain more or less constant, because we're moving further away from the transmitter, and our field strength has halved. Our power flux density must reduce by some amount. Is it going to reduce by a factor of about √2? Well, no, we've just discussed it reduces by a factor of 4. Divide the side of the square by 2, divide the area by 4. Similarly, have halved, also no, because it's not the same as the field strength. It is a way of measuring the intensity of the power over a square meter area, and we're left with have reduced to a quarter of its initial value. Well, as we discussed, we halve the field strength, or we halve the length of the side of the square. We're going to divide the area of the square by 4, and in turn divide the power flux density by 4. Let's skip down to the answers, see if we've got that right. I hope we have, and we see that, of course, for question 35, it is, of course, answer D. Thank you very much. I'll catch you for the next one.